Hi, everyone. This is the Hungry Math Professor here, and thank you for coming to my channel. And today I want to do a little bit of a discussion going back to one of my favorite topics of Gödel's theorem. And I want to elaborate on something I brought up before about Diophantine equations. And I want to just paint a picture of some tension between what it means for mathematical statements to be true. But just to be clear, I'm not going to go over Gödel's theorem again, like what it says and what the setting is. So I'll link to the video where I already kind of talk about that in quite a bit of detail. In particular, I use this book that I'll also link to again, which I'm going to specifically be kind of elaborating on one of the chapters and one of the facts that's brought up there. So first of all, let me just say a little bit about what a Diophantine equation is. So Diophantine equations. Well, in the most generality, it's an equation of the following form, which is going to feel a little bit unsatisfying if you don't already know what they are, but then I'll give you some examples. So if I use capital P to stand for a polynomial in however many variables I like, then I'm going to, it's a polynomial equation in n variables, and it's equal to 0. And what makes it Diophantine is where we look for solutions x1, x2, all the way up to xn, which are all integers, right? So, integers are a set of negative whole numbers, 0, and positive whole numbers. Okay, so specifically, if I look for integer solutions, then we're talking to polynomial equations, then we're talking about Diophantine equations. So, it's helpful if you're not already familiar with this to have some examples. So, for instance, Pythagorean triples, x squared plus y squared equals z squared. Now, okay, I use x1 through xn in the description, and then I immediately move to xyz. But okay, I can write this in the same notation if I like. So that's a Diophantine equation. And we know that there are many integer solutions. They're called Pythagorean triples, such as 3, 4, 5, right? Another example, famous example, is if you take x to the n plus y to the n equals z to the n, where n is a natural number which is bigger than or equal to 3. This is called Fermat's last theorem. Fermat's theorem. And it was proven to to not have integer solutions, but it's one of these proofs that took a long time to establish, even though it's very simple to state. And so this is a good example of a Diophantine equation. Okay, great. What else? So we should give a few more examples. Oh yeah, by the way, I should say it was proven to have integer solutions by Andrew Wiles in 1995. Okay, so that's a fun example, but Diophantine equations can come in all different forms. And so, for instance, I could take x1 squared times x3 plus x2 cubed x3 to the 7th plus x1, x2, x3 equals 0. That's an example. And I could use any number of variables that I like. but I can't use infinitely many. I can only use finitely many, but I can use any number of finitely many variables that I like to describe one. And I can do all this funny things with polynomials, but I can't do stuff like take the cosine of x1 times x2 or tangent or e or anything like that, right? It's got to be a polynomial, which is formed by multiplication or addition of these variables with coefficients. Okay, so that's what Diophantine equations are. And if you remember, the punchline of Gödel's first theorem is that any system which can describe number theory has statements which can be made which are undecidable, so that we cannot prove that they're true and we cannot prove that they're false. And so, again, as I've said in this other video, the first kind of follow-up question you might have to that is, okay, but are there any interesting statements that are undecidable? And one of the statements that I showed you that is undecidable that I think is interesting is the continuum hypothesis. But I'm not going to really talk about that here. And so the other statements that are at least seem mathematically interesting, or at least certainly mathematical statements, they're not just like self-referential statements that you can make in first order logic, are statements about Diophantine equations, right? So let me try to bring us to that kind of question. So now the question we can ask for any Diophantine equation, so given any Diophantine equation, P of x1 through xn equals 0, we can ask, can we prove that the equation has or does not have a solution? Okay, and I think I mentioned this in the other video on Gödel's theorem, which is that they're always a consequence of or another way of formulating Gödel's first incompleteness theorem is to say that, so it's not exactly an answer to this question, but it's certainly an answer related to this question, is that there are always infinitely many Diophantine equations for which we cannot prove that they have a solution and we cannot prove that they do not have a solution. Okay, so there are infinitely many Diophantine equations which are undecidable in the sense of deciding whether they have a solution or not. And these are certainly mathematical statements. They're not like statements of purely of first order logic. I think anyone who agree that asking whether or not a Diophantine equation has a solution is certainly a mathematical question. Now, whether it's the kind of question a mathematician actually cares about, I think is a completely different story, because there are lots of Diophantine equations. And it's true what I said in the very beginning of the video, that Diophantine equations have been studied, for a very, very long time in the history of mathematics. But we don't study every Diophantine equation. We've studied special ones. And even to this day, there are special classes of Diophantine equations that people study for special reasons. And so, someone could object that perhaps the ones that we can't decide are somehow the uninteresting ones in some sense, right? And I'll admit that the proof that is used to show this answer cannot actually exhibit a particular Diophantine equation as I understand it. So, these are some caveats, but I want to take this and instead use it to produce some tension about what it means for mathematics to be true. Because let's just say, this statement I gave is actually true for any system which is rich enough to be able to express Diophantine equations. So that means you need, multiplication, addition with some reasonable properties. And so, for instance, if you can describe number theory, then that's reasonable. So, but you can also just say for ZFC, for instance, this result applies to ZFC, right? So applies this in particular applies to ZFC, which is the default sort of foundation for mathematics that I think most mathematicians will fall back on if you push them hard enough. But for the most part, we don't really need to work with it in any kind of serious way. Okay, so you could say, well, I just think that the statements are true are what can be proven in ZFC. So if you can't prove it in ZFC, then I wouldn't say that it's true. I think this is a perfectly reasonable, practical position to take. I think it opens you up to some kind of formalism about, formalist position, and then I have to push you to wonder, like, okay, but what makes CFC special? Like, are you just saying that anything that follows from a consistent theory is true? I think that's a defensible position, but it might come with some uncomfortable consequences. I don't want to go too far down that road. I just want to point out some tension here between this particular point of view. And this is the following case. So, of course, given any Diophantine equation, so there's two possibilities, right? So given any Diophantine equation, right, either the equation has a solution or it doesn't, right? It almost feels silly to write it again. But so case one, assume D, oh, I'm switching my notation, sorry. Let's assume that this polynomial equation has a solution. Okay, so let's assume that this polynomial equation does have a solution in the integer. So I can pick integers x1 through xn, plug it into the equation, I get 0, right? Well, in that case, there has to be a proof, right? Because, for instance, if I take n copies of the integers, then I know that this set is countable. So we can list out the elements and try them one by one until we find a solution. Yeah, we just keep listing them out one by one. And eventually, if a solution exists, we'll find it, right? Now, that's not elegant proof at all. It's a brute force proof. But when it comes to whether or not you can prove something in a formal system, the proof doesn't have to be pretty. It just has to exist. And maybe there is a better proof, as well. But at least there is one proof which can be exhibited by just trying every element until you find one. And in general, proofs have to be finite in length, but notice this proof will always be finite in length because eventually you'll have to have found it and you'll stop. And although it might be very large, it's certainly finite, right? So this is where the tension comes in, because if you have a Diophantine equation and it's undecidable, then it must be the case that it does not have a solution. Because if it did have a solution, you'd be able to decide. right? So, okay, now we're in case 2. So assume P of x1 through xn does not have a solution in the integers. When I say it has a solution or does not have a solution in this particular video, I'm always talking about in the integers because we're talking about Diophantine equations. Well, then there's kind of two subcases here. So there's case 1, which is there is a proof in our formal system of this fact. And then there's case 2, which is there is no proof in our formal system of this fact. And what I said earlier is equivalent to the following refinement, which is to say that there are, so there must be infinitely many Diophantine equations which do not have a solution, but which are undecidable in our formal system. So again, my goal in this video is to uh, paint some tension for you between what it means for mathematical statements to be true. If you want it to be the case that what it means for mathematical statements to be true is it follows from ZFC, then this paints some tension for that idea, right? Because there are Diophantine equations which I know cannot have a solution, but yet I cannot decide them in ZFC. I can't demonstrate that fact in ZFC. And so it tends to make you feel like there is a notion of truth, or there's some other sense in which mathematical statements can be true, which are not captured by ZFC or not captured by um, a particular formal system, right? It turns out Gödel was a Platonist himself, and not exactly for this reason per se, but I think in the spirit of the reason that I'm pointing to here, he felt like there has to be the natural numbers have to have some existence, in some Platonic sense, or I don't want to put too many words in his mouth, but he believed that the natural numbers have to exist in some sense, and it's that the fact that they exist, which causes these statements to be true or not, right? So, if the natural numbers really have some being, some existence outside of a formal system, then that's what it means for a Diophantine equation to be solvable or not. It means for the actual natural numbers, right? And these formal systems are trying to capture the mathematics of the actual natural numbers, but they are failing or are slightly inadequate in the way that Gödel's theorems and other theorems after it point to, right? So again, it's this question of whether there is some notion of truth that is not just captured by a formal system, not just following from a formal system, but is capturing like what the natural numbers really are, what the integers really are. Or, is it the case that that doesn't really make sense? And, what does it even mean to talk about Diophantine equation outside of a formal system, right? I think this is how someone would attack this from the other direction. What does a Diophantine equation even mean if you don't describe for me a formal system, right? And so, you can say that it doesn't have solutions outside of this, but what is that? Are you now arguing in some other formal system when you do that. So my goal here is not to, completely show you the answer, because I don't know the answer to this, but instead I want to paint some tension, because I think it's very tempting to just fall back on ZFC. And from a very practical standpoint, I think this is a completely reasonable thing to do, and what I do as well as a mathematician. So I don't want you to misunderstand my point, but I think there's a bigger sort of philosophical question, which is not answered by that sort of default fallback, which is whether or not there is some sense in which mathematical statements are true outside of a formal system or not. Now, I've always, had a hard time with Platonism, just because I think it's bizarre to sort of postulate some Platonic realm, and so I always find that to be quite bizarre. But I actually find this kind of argument about Diophantine equations and formal systems at least uh, helpful, in the sense of giving me some reason to think that it's at least a reasonable theory to have on the table. Now, I personally want to remain agnostic to this, because I see no reason to commit to one way or the other. But in my agnosticism, I'm acknowledging the fact that there are multiple, ways to see this problem, and it's not just as simple as saying whatever follows from ZFC is true, right? So anyways, I wanted to paint some tension for you. I hope you found this interesting. If you disagree, or you want to poke to some other potential way of solving this issue, I'm happy to uh, listen to your comments and let me know what you think. Like, comment, and subscribe, and I hope to see you at another video.